So thank you very much, Dr. Park, for this very nice introduction. Well, I would like first to thank Professor Kajita, with whom I had the chance to work next by, and he told me, he taught me a lot. And thanks again for HRP2. This is a wonderful robot. And I would like also to thank all of you guys, because I think in the new robot that you see here in the presentation, which is Talos, and now a product, I try to take what I believe is the best. I'm not sure if the result is fully complete, but this is a robot that you can buy. And I've been trying to talk with Nikos Sagarakis and other very nice lab doing nice mechanical system. And I think most of the times the problem is support. I think even if Boston Dynamics is not selling Atlas, is because if you break it, being able to fix it means that you have to be close to the workshop, and this is a big problem. I really enjoy in Europe the fact that we have DLR and IIT, but still being able to build this kind of European, lab where people like us who are mostly doing motion planning could try stuff, break the robot and send it back. It's super difficult. So I'm find myself extremely lucky to be able to work with PAL Robotics, where we are nearby, so it's only 3 hours to send back the robot and we can fix it. So the robot is not perfect, but I think you all know that human robotics, specifically hardware, is super difficult. So we tried our best to improve it. I'll try to show you how we see motion generation in terms of scientific problems and how we can, as much as we can do, propose some solution. So the goal that we have is depicted in this picture. So it basically, we want to see Talos being able to go inside a kind of lab environment where basically we stairs, and we want, like the robot, in real time, being able to, whatever his situation, being able to generate in real time this motion. And I think you all are convinced that this is very hard. If we look, for example, at the very nice talk of Kajita-san on DRC robot, specifically climbing stairs in multiple contacts, I think is still a very hard problem to do. Like, so if, for example, if you take the ROS navigation stack on a mobile robot, it's like, I mean, now you have companies who can take this navigation stack, put it on their robot, and it works. But it's including a lot of SLAM system, base estimation, model predictive control. And our dream here in this picture is to try to do this in 3D on humanoid robots. And this is a big scientific challenge, but this is what we are aiming at. So the classical architecture usually is the following one. So in orange here, you can see the classical perception loop that I will not talk about because I think it's kind of big problem in itself. I will mostly focus on the blue one, where you can see that based on the perception loop, what we usually do is motion planning. And then from this motion planning system, you generate a central dynamics model predictive control trajectory optimization that is sent to a stabilization system. And then you have a whole body QP controller, which is sending the command on the robot. And there is some application that I will show where from motion planning, you have directly a kind of finite state machine of control which can be connected to whole body controller, the QP architecture. And we had a nice example previously with the presentation of Dr. Ginoli. So what I will try to try, what we believe in the Gepetto team is that the 3 last block can be completely actually replaced by a whole body predictive control. To be honest, if you asked me the question 8 years ago, I would not believe it was possible because it means solving at a very high speed, very complex, nonlinear optimization problem. And what make us change our mind was the work of Mujoko from Emoto Dorov. And from then we worked as much as possible to make this view possible. So in terms of integrating manipulation, motion planning and task, what we have been doing is basically take a human robot like Talos, where you give him an initial configuration. in front of a box, and basically you want the robot being able to find by himself a sequence of control. So the task, I think you are all familiar with the notion of task, where you build a kind of QP based on a sequence of tasks. And finding this task by itself is still a very complex system. And what my colleague Florent Lamiro, who is in the bottom left, developed is basically a very fast way of exploring a set of constraints based on a compact graph where you just say the robot how he can manipulate an object, and where the objects explain how he can be manipulated. And the system will take the task and explore by itself the sequence of constraints and generate a controller here. So it may, for you, it may be quite easy, but with Talos, we still have some calibration problems, not with the legs, but with the upper torso. And actually, if you're not planning task, visual servoing task, you cannot actually do this motion due to uncertainty and flexibility inside the system. So right now, I think it's very powerful for industrial application, where basically you can have less complicated robot, where basically you just give the initial state, the final state, and the finished state machine to generate the whole control can be automatically generated. Well, there is still some limitation, but I will not go too much into detail. Again, this is the direction we are taking. So otherwise, to come back to the structure I was showing, what is usually done is to simplify, to break down the complexity of the problems. What we usually do is we have a reachability planner, which is basically planning trajectory for a upper body, which will not be in collision, but has unit contact. You still need to make sure with the green part that your limbs are in contact with the environment. So from that, you can find a sequence of contact. Then what you try to do is to find a center of mass trajectory, which is consistent with the centroidal dynamics. I think nowadays this is well known for at least planar robot, but we start to have at least 2 or 3 algorithms for 3D multi-contact system, and then to do whole body force control. So this pipeline from left to right is well known. The problem is if something is not working well in one of the steps, you have to come back manually on the other footsteps. And what we would like to do is basically break down this need to have the human fixation on these steps automatically. And this is why we are trying to go towards trajectory control. So basically you end up with this kind of software architecture, which I think is quite classical. And the base for us will be to try to have the state, do whole body model predictive control, send it to an instantaneous store control, and send it back for the robot with an estimator to have the real state of the robot. And this is done in the frame of the H2020 European project called the Memory of Motion, led by Nicolas Mansart. And the point for us is to generate this, to develop this generic methodology for complex motion applied to the Talos robot, an exoskeleton, and the quadruped animal at Oxford University. So just briefly, I will try to focus on 3 parts: whole body MPC at 100 Hertz on the real robot, preparing torque control locomotion, and what we call memory of motion to break down some of the, what we found out are the main problems with trajectory optimization for model predictive control. So here, to briefly state what we mean by model predictive control, this is a classical trajectory optimization, where basically here you have the cost and the constraints, where we try to minimize the state. What we try to find is the state and the control submitted to the dynamics of the system. And here this is whole body dynamics with multiple contact. And we also try to optimize the time. The point is that here the difficulty is that we have thousands of sparse variables. So to make it efficient, what you need to do is to focus on the sparsity. And for this, the dynamical differential programming is very efficient. And we try to have a first simplistic implementation, taking into account the dynamics of the system. Now, what we are working on, based on this very simple algorithm, we are adding more and more constraints on the system. And I think a lot of people are familiar with SQP-like method, and we think that maybe it's not appropriate. So we are working mostly in penalty-based algorithms, which are augmented regression. And actually, the engine that we're using for that is Pinocchio. So we are the children of Roy Featherstone, who I think is in the audience. So thanks you very much. Your book is our Bible. And we have been working, I think, on 5 implementation of your algorithm to make them more and more efficient. So I think now we're going toward a very stable implementation. Up to, so for example, here you have the inverse dynamics. So we are up to 3 microseconds to compute the inverse dynamics, even on robots such as Talos or Atlas. And the forward dynamics is, again, less than 7 microseconds. And we have derivative of the algorithm, which are very important to have the sensitivity when you are using dynamic DDP. And we use code generation, which allow us to reach this kind of nice time. And this is a basic engine in our an open source trajectory optimization algorithm, which is BSD. So you can use it and do product with that. There is no problem. Which is called Crocodile. And it's a dedicated multiple shooting DDP solver. And here you have application on animal. So we still have some constraints. So for example, our main work now is on collision. So we're not handling collision. And probably this is why we are able to generate this kind of motion quite easily. The big point here to Todoro works is that we are giving contact phases. Okay, the contact phases are not discovered. I think it's a very high level of complexity right now. So this is maybe the 2 main limitation of this very nice work, is that it's including the whole dynamics, the multi-contact dynamics, but phase has to be provided, and we're not handling yet collision. What we've been able to do is to consider an horizon of 100 nodes. So you can then after change the control time. It has been done on a i7 3.2 gigahertz CPU with code generation, very important to have something extremely efficient, and on 6 threads. So I think this is not something that is readily available on any robot. Even on Talos, we had to plug and connect another computer to have it. Still, I think in research setting, it's still something that is easy to do and not too costly. And what we got is MPC on iCub at 308 DOF and 100 Hertz on Talos. And the most costly part is a backward pass when you are propagating the difference between the state that you wanted and the desired states. You modify the control part. This is the most expensive for now. So now based on this presentation, I've implemented this on the Talos robot, and here are some motion. So I'm sorry, Dr. Park, they are not super impressive compared to what we have been. But this is torque control. The torque control is working at 2.3 kilohertz, and you have MPC on top of this with state feedback. So I think for us, I believe that this is one of the first time we see whole body MPC working on a robot in torque control. Tough work to do, but it's feasible. So we are very happy about that, and we think we have the basic bricks to go forward. So just one thing, I lose track of time. So if I'm going over the limits, please feel free to stop me whenever it's needed. So the next time for us is to go toward the torque control locomotion. So based on the MPC or motion, what we would like to do is to have a QP-based task space whole body control to go towards torque control. And this was so this is the work of our partner PAL Robotics on the robot Talos. So here on the right, this is the outcome of our work on planning dynamical multi-contact, non-coplanar multi-contact system. And this is, so basically we have the center of mass trajectory, the position of the feet, the desired position of the feet, and this is with the ZMP, center of pressure. This is sent to the whole body control, and in real time, it's executed on the system. So here we did it 7 times on our robot. It worked 5 times on 7. And maybe you can see it, but the robot very often slightly hit the stairs, and he's able to recover from that. So it's quite nice. What we know with Talos is it's not as precise as HRP2 or maybe HRP5P. There is flexibilities. We have still some low-level problems to solve. But it's nice to see that we now have a robot that can be shared between laboratories. So we are up to, there is 5 laboratories now who have Talos. And we are sharing our know-how and code whenever it's good to be able to work and on top of this robot and what we're able to achieve. And again, Pan Robotics is very open in improving, modifying the hardware, so it's very nice to work with them. So still there are some primes. Well, we have the classical primes of harmonic drives. There is flexibility, there is some implementation noise in the joint torques, and due to some choices on the system, we have a low frequency between the joint torque sensor that I think DLR on maybe Command Plus and Walkman are not suffering. So for us, it was a primes because it's very hard to change once the design has been done. So we are working on open hardware project, going to the what the Kajitas says. I think it's very nice to have open hardware project where students can go, they're not afraid of the robot, they're not afraid because they have this 100 kilo robot falling on themselves, and which is costing super high. So here the key part for us is that it's again a collaborative project. So everything is open source. The open hardware, the firmware, the control, you can use it. And as a partner, Gepetto provided the electronics through one of our postdoc. And the nice stuff is, I don't know if you see, but you are able to jump 5 times the height of the robot. So I think it's a nice research tool. It doesn't have all the prompts of human robotics. I think human robotics is way much difficult than quadruped robotics. But again, in intermediate stages, I think it's nice to have this. And recently, Dr. Majid actually he built a nice biped robot based on the fundamental brick. And the robot right now costs 12,000 euros. So it's a bit expensive if you want to do it by yourself, but for, I guess, academic or university, it's affordable. So we build this control board, and which allow us to implement our own low-level control work. So for example, the Elmo board is completely closed. You have either position or torque control. If you want to add speed and stuff like this, it's always very messy, very difficult. So here it's open source. So you can do whatever you want. It's kind of cool. And for us, the target is to reach 10 kilohertz in the local control of Talos. Okay. One thing is with DDP is that what's happening is that the space of trajectories you can do with differential dynamic programming is huge. I mean, if you look at, for example, what Yuval Tassa, one of the students of Emo Todorov, has been doing with DDP, it's super impressive. He's generating thousands of motion. So what we find out is that it's super difficult actually to tune the weights of this DDP when for your robot and for a specific application. This is a nightmare. Actually, it's one of the first experiment we did 6 months of weight tuning, just weight tuning. So for me, it's really bad. And this is where AI come into play. We really need to be able to explore the state space of this kind of algorithm and have a compact way of finding the right weights, the right warm start for this kind of DDP. So here you have a data set based on this simple setup that I showed you, which is basically, it's open source. You can download all the 3D parts and build by yourself if you want. We hope it's a benchmark. So for example, the debris I showed you before, we have at least 3 labs who have it and who are trying to test their algorithm. So I think, again, benchmarking for this kind of stuff is quite nice. So the point for us here is that you have 2 mathematical objects when you are dealing with this optimization. You have either the trajectory optimization or the policy optimization, which is archive reinforcement learning. But one is the dual of the other. So if you like inside DDP, basically you are optimizing the feedback gains and they generate this trajectory optimization. So what we did is we used our tools in terms of planning to actually explore the state space of a simple, here this is a dynamics of a 2D inverted pendulum, which is here unstable and has two stable states here. And what we did is we sampled these kinodynamic states, use a trajectory optimizer like ICCAS2020, who are generating for us this kind of optimization, breaking, I mean, half of the times. So it's kind of costly. And what we did is we basically sampled the subtrajectory, the state space, the value function. And what we did is we used the neural networks actually to learn this 4 information and used it actually to explore more efficiently the roadmap of the state space. And this algorithm is called IREPA. And what we did is, so we applied it efficiently for quadcopter, and the problem is that we wanted to extend it to a humanoid robot, and due to the fact that the humanoid robot has much more degree of freedom, the scaling is kind of difficult. But what we did is we used crocodile and much more trajectory. And what we used is we use PyTorch actually to learn this, the value function, the derivative, and the policy. We build a huge virtual space based on what you have seen, the same setup that you have seen before. And the output is the following one. So now the neural networks is basically bootstrapping the DDP actually to generate a feasible solution. So instead of all the times, as you do classically in motion planning, rediscover the whole world and what you do, you use the neural networks as a kind of oracle to bootstrap your optimization algorithm. And why you are coupling one of the other is, as Kajita-san said previously, the problem with neural networks is always approximation. So when you have a solution, it might not be feasible. It's an approximation. But the point is that if you put it with a Lagrangian system like the optimization, he is very efficient at finding a feasible solution because he's very nearby the optimum. And I think this concludes my talk. I would like to thank the team because, of course, this would not have been possible alone. So here you have Nicola and all the PhD students who help us to make all this nice video and work.